The earth science teachers here at DSA got together and collected science must-know items, such as how to write in scientific notation, and what is and how to handle significant figures. Please review this information carefully. You might recognize it, it may be new to you. Take notes if you don't easily recall it. It is very important to your future science endeavors that you know how to handle measurement and calculations in the real world. It all comes down to accuracy. How detailed can you be and still keep it real? The objectives of explain what are significant figures, give you some measuring guidelines, rules for how to handle significant figures when performing calculations. We'll recall the rules for rounding numbers. I've ended with some sample exercises. First, a bit about numbers. You need to realize that all measurements are approximations. When you read a ruler, does the paper stop exactly at the line? Or could you haul out the microscope and detect that the paper is ending a hair to the left of the line? Even if the paper ended precisely on the line, how do you know how well made the ruler was? No measuring device can give perfect measurements without experimental uncertainty. For one thing, it's too expensive. We get plastic rulers that expand and contract slightly with the room temperature. Are there more precise rulers available? Yes, but at hundreds of times the price of the one we use. Measurements then are about good enough. For our purposes, measuring a paper to the centimeter is good enough. For the space shuttle, you might want it to more accuracy. Good enough depends on what you are doing. When you are doing measurements, by convention, which means agreement among everyone, or a distance measured to 11.6 centimeters is said to have an absolute uncertainty of plus or minus 0.1 centimeters. It could really have been 11.7 or 11.6 centimeters. We are somewhat uncertain about that last digit. If we were more certain, we would have written 11.60. Significant figures is simply the number of digits that are known with some degree of confidence or reliability. The number 77.2 has 3 significant figures. If you add another digit, you are increasing the number of figures that you measured. Test yourself. How many significant figures does 77.23 centimeters have? Pause if you would like to have a few more moments to study the question. 4 significant figures. How about 4.5 grams? 4.5 grams has 2 significant figures. How about 2 gallons? The 2 is just one digit, so it has 1 significant figure. 6 significant figures. All non-zero digits are always significant. For how many significant figures are in 342 milliliters? 3. How about 2.4 milliliters? 2. Zeros between non-zero digits are significant. By the way, write these guidelines down if you don't recall these. So how many significant figures does 3,005 kilograms have? 4 significant figures. 6. Leading zeros just show placement, not significance. So it's fairly easy. If you've got 0,004 miles, it only has 1 significant figure. Those are leading zeros, you can just ignore it. 0.0008 meters, again, only has 1 significant figure. The zeros in front of the digits, you just ignore them. They're showing the placement. Trailing zeros are significant. 0.20 milliliters has 2 significant figures. If I'm going to take the time to write the 0 after the number, then you're going to assume that I measured it. Here's an example. Pause if you want to see this some more. It's talking about non-significant, the 0 for cosmetic, because you really don't have to put a 0 before the decimal place. But the zeros after the decimal place are only to push it to the tens, hundreds, 1,000th place. It's not to show that you actually measured that accurately. However, afterwards, it is showing significance. Whether it's 0 or non-zero, the minute it had a non-zero digit, you are assuming that was measured. Yeah, there are some times when you're looking at the number you can't tell if it's supposed to be significant or not, such as when a number ends in zeros that are before the decimal point, you can't tell the degree of accuracy that was used in the measurement. 100 miles may have 1, 2, or 3 significant figures. We can't tell if it was exactly 200 as they measured it, or they just measured it to the nearest hundredth. Scientists use scientific notation to avoid these scenarios. Scientific notation, which is a different lecture, avoids these scenarios by writing it 4.02. Any digit you write is assumed to be a significant figure, and then you multiply it to get that place value. What about non-measured numbers? Non-measured numbers have an infinite number of significant figures. This means that we can add as many zeros as we need to match the other measured numbers for calculations. By definition, 12 inches are in 1 foot, or perhaps you counted it, 31 students in a class. No accuracy problem there. You don't have 30, you don't have 32, you have 31 students that were counted in a class. These don't add or detract for the number of significant figures. So now we're ready for the calculations. So you've measured a couple numbers, and maybe you have some numbers by definition, such as the 12 inches to a foot. How about your result? Well, here's the whole reason we've discussed significant figures. I have many students who report that a measured slope of 1 divided by a measured slope of 3 is 0.3333333. Well, what's wrong with this? Did you really measure your values to that many digits? Of course not. We have better things to do than get that accurate. We're not trying to send anybody to Mars. Take note of this and remember it for the rest of your life. Your result cannot be more accurate than your least accurate measurement. This is the meaning of this entire video. Memorize it. Apply it. This applies when you are using measured amounts in calculations. Again, your result cannot be more accurate than your least accurate measurement. The first step is to determine the significant figures for each number used in the calculation. You're not doing the calculation, you're just checking how many significant figures there are in each element. Step 2. Calculate. Use all the digits. You don't care about significant figures when you're doing this part. Step 3. Now you need to round your result to the smallest significant figures. In this example, the smallest significant figure is 2. That's the 3.2 had 2 significant figures. So 78.048 is meaningless. It has too many digits. You did not measure everything to that degree of accuracy. So it's inaccurate to pretend that you did. You can't. It's just not allowed. You can only have 2 significant figures. So you round it. 78.048 becomes 78. Let's review the rules of rounding just in case you might have forgotten. If it is 5 or greater, increase the last retained digit by 1. So 34.6 becomes 35. If it is less than 5, the last digit is unchanged. So 4.4 becomes 4. If you're using a calculator, keep all the digits throughout the calculations. Only round the final answer. Let's try some examples. All set? Are you comfortable? What are the number of significant figures for the following? Take a minute. Pause if you need to. 5. That has 3 significant figures. The 4 is 1, the 5 is 1, and the 0 after the 5 is 1. Because we measured, otherwise we wouldn't put that 0 there, remember? How about this one? Again, you don't do the calculation. 4.2 has 2 digits, therefore it has 2 significant figures. How about this one? Remember, if it's scientific notation, all those zeros are showing you measured to that value. So you have 5 significant figures. If you had only measured 3 significant figures accuracy, you'd just put 10.4. How many significant figures should the following have? Again, don't get out the calculators yet. Look at what's being asked, not the result, but how many significant figures should the result have? Okay, so here's 3.24 times 5. You find the small significant figure, which is the 5, which is 1 digit. So your answer can only be 1 digit. You can't be more accurate than your least significant figure. You have just 1 in that first number, and you have 2 in the second number. So if you said you just have 1 significant figure for your result, you'd be right. You'd think maybe that'd be ambiguous, but it's not really, because they put the 0.0. So you're assuming they measured 600.0, that many spaces. So that would have 4 significant figures. And the 40.2, that would have 3 significant figures. So the least significant 3 digits. Again, we have a decimal point in there. So the digits after it, that 00, that 2 for the 200, that means it's 1, 2, 3, 4, 5, 6 significant digits. And then the second number has 1, 2, 3, 4, 5, 6 also. So therefore 6 significant digits for your answer. Sources to go. This one has a quiz there. It's fun. Enjoy it. Pause if you need to get that site. This one also gives instruction on how to do it and grades you on your answer. How many significant figures are there? So if you'd still like a little practice, this is a great site to go to. This site I liked because they had more than just significant figures. They talked about size and scaling and the whole measurement problem that you need to worry about. Where I got a lot of the rules from is this site right here. I hope you've enjoyed this on significant figures, and now that you feel confident and try it, do it yourself. If not, go ahead, rewind, and play again.